Hi, my name is Adolfo Jasso Campos, and today we explain the experiment of the Archimedes principle. So first of all, we need to understand what is pressure. Pressure can be defined by the formula of a force divided by some area. For example, when we talk about ambient pressure, it means that in a specific area, for example on this one right here, the air, as it weighs something, it makes a force downwards. So therefore, if we know this force and we know how much this area is, we can get the pressure. But this also works when there's something submerged in a liquid. For example, here on a pool, we have any object of any form right here, and this can be seen as a displacement of the water that it used to occupy the space. So because this new object that was introduced in the pool displaces the water, therefore this water wants to return. So it makes a pressure on all points of the object inwards. But when we only want to know the pressure vertically, therefore we don't care about the horizontal axis, we can actually reduce enough in order to make a very useful formula. So for example, here we have a sample, in this case of water in the pool, which is below also some air. So this sample obviously has some volume, which means it has some area right here, like this for example, and some height, this one right here, which will be this right here. So if we would make a free body diagram of just these vertical forces, we get our three forces in charge. First, the force made by the weight of both the water and the air, in this case, all this force right here. Secondly, the weight of the object in itself, because any object that has mass has a weight. And second, this second force right here. This force appears because, as I said, all the water wants to occupy that space. So therefore, it makes a force inwards to the object. This means that from downwards, the force is pointing up. So this will be the second force right here. So when we have an object like this in equilibrium, fully submerged, we have that all of these forces cancel each other out. So we have two downwards forces, force 1 and the weight of the object, and force 2, which is going upwards. But as we know, this weight will be of this fluid itself. So therefore, it can be it can be separated on the mass of the fluid or object times the acceleration of gravity, which is g. And then we can replace these forces with the formula for pressure. You just multiply them by the area. In this case, it will be this area right here, from the top and the bottom, respectively. But in this case, we're assuming it has the same area. So we just call it A. And we can replace the mass of the fluid by its density times its volume, as density times volume is mass. So we can also separate this volume on area times height, as that makes volume. Remember, this height is this weight right here, and there is the same area for all of this. So therefore, we can cancel area on all of these three variables, and we get that the difference in pressure 2 minus pressure 1, is equal to the density of the fluid times gravity times height. So this formula applies when you submerge a fluid on another, maybe water on air or oil in water, etc. But this has to be fully submerged in order for this formula to work. But we can also get a new force, which is called the buoyant force, which will be this force 2 minus this force 1. This will be, ignoring the weight, the total force that pushes the object upwards. But when an object is fully submerged and in equilibrium, this buoyant force, which remember is this part right here, will be exactly equal to the weight, as they will cancel each other out. And as we saw, this is the mass times the gravity. So therefore, if we introduce an object or fluid, etc., we can separate all of these using the previous procedure, in order to get the density. We only get the density and the volume that matters. But as they occupy the same volume, this can also be cancelled out, and we get that the density of the fluid has to be equal to the density of the object. In other words, if we put an object inside, for example, water or any fluid, and this object is in equilibrium, it doesn't sink and it doesn't float, therefore the density of the object has to be the same as the one of the fluid. But this only happens when it's fully submerged and it's equilibrium. What happens if it isn't fully submerged? For example, the object is floating, like right here. In this case, we have, for example, wood on water, and as you can see, only some part of the wood is inside the water. This can be seen, for example, as boats or when you float under the pool, etc. But here, the same formula applies, except it's not the fully weight of the object that matters. In this case, the weight will be the apparent weight. This is the weight that the object seems to have when it's submerged underwater. Okay, so how does this relate with Archimedes' principle? Archimedes' principle tells us that when you introduce any object inside a fluid, as I said, it displaces the original fluid that was right there. So therefore, the whole volume of the fluid has to expand. For example, if we put this object even deeper, this water level would need to rise in order to account for the space the object is now taking. So Archimedes says that this displacement can be used in order to calculate the density, as we will know the displacement and the apparent weight. So therefore, we were going to use this in order to calculate the density of water. So here is a mock-up of the experiment. Here we have some object, and we know the object weight and its volume, and we will put it on water and see how much the water level rises. This will tell us, by knowing the area of this container right here of the water, times the change in displacement, the volume this object occupies. So therefore, by knowing that and knowing the proportion of the real volume to this displacement volume, we can get the apparent weight, which will have the same relation with the real weight of the object. And if we do this multiple times, we can get a graph that tells us a relation between density of the fluid and the space this object is occupying. So for example, if we put inside an object which is denser than water, we can have it be just on the surface, just put a little of it, and see how much the water needs to displace. And by knowing this weight of the object in itself, we can therefore use Archimedes' principle to see how much that water will need to be inside in order to make the same effect. So therefore, we can get how much water is displaced, and therefore we can know the density of the water by using the formulas I showed previously. But if this object is denser than water, then it will sink. So therefore, we need to sustain it with something. Example, this string right here. So this string can actually be connected to a sensor that tells us the weight is pushing down. So therefore, we will have the formula, which will be in equilibrium, of that the buoyant force will be equal to the apparent weight, which will be the weight detected by the sensor right here on the top, minus the real weight. This is the force that will push it upwards. So therefore, we can calculate using all of this the buoyant force, as we already know the weight, and this will tell us the apparent weight. And with the buoyant force, we can make calculations using the previous formulas in order to get the density of the fluid itself. Okay, so here are the two objects we're going to use to make the experiment. Here we have a cylinder. Here you can see the diameter it's being recorded in order to get the volume, as well as a prism, which also has the same object being recorded. So here is basically how the experiment was made. As you can see, here we have a container which is filled with water. We at first recorded how much this water is at a certain level, and then we introduce part of the object. As you can see, it's being introduced right here. This is the object, in this case is the cylinder. And we measure with this measuring tape how much the water level increases. At the same time, we're using Pasco in order to know how much a force sensor is feeling the weight of the object. As you can see here, we can wait for the graph of force versus time in order to get horizontal, in order to know this, which will be the apparent weight at this time. So with this, we have all the information we need. Here we have first the diameter of the container as well as the cylinder and rectangular prism. With this, as well as the masses. These are the masses, as well as the diameters we calculated previously. We calculate the areas of both the objects, in this case cylinder and the prism, as well as the container, and subtract them. This because when we have here the container and the object being introduced in it, as you can see, the area of which the water has in order to rise, which will be the full area of the container, minus the area occupied by the object. So therefore we need to subtract these two areas to get the real area being used on these formulas. Sorry, these are uncertainties. Here is the real areas used. So then we have our calculations. Here is the difference in height on here, these ones right here, as well as the apparent weight that the sensor recorded, which will be these ones right here. So therefore we can then subtract each of these with the specific weight using these masses right here of each respectively object. From there we can therefore know the buoyant force. So when we plot this buoyant force against the change in height, we get these formulas. This one right here is for the cylinder, and this one right here is for the prism. As you can see, they do follow a linear tendency very closely, which is in accord to our formulas. And here we have that the slope is around 17.9 in the case of cylinder and 17.3 in the case of the prism. So by using this formula right here, as we know, the buoyant force is equal to the weight of the fluid which is occupying, which is equal to the mass times g, is equal to the density times the volume times g. And we saw volume is equals to area times height, so therefore the buoyant force is equal to the density of the fluid times the area times the height times g. So as you remember, we plotted h as the x-axis and buoyant force on the y-axis. So therefore our slope will be the density, which is what we're going to try to get, times the area times g. So we just need to divide that slope by the area and the gravitational acceleration. So here is the results. As you can see from the cylinder, which is this one right here, and the prism is right here, we got a density of around 5,455 kilograms per cubic meter and 1,163 kilograms per cubic meter. This is kind of bad, as they are really far and they should be the same, as they are recording the same thing. And we can see down here the real error of the cylinder, which was around 500% of error, while the prism was only 16%. Okay, so why did we got this incredible error? Well, first of all, the system is very sensitive. As we're using really small values, any small change can change a lot. For example, if the weight of if the area of the container is a little bit smaller, just 0.002 smaller, the error will reduce from 500% to 300%, which is a lot of reduction by a really small value. So any small error in that calculation can alter. As you can see, there are a lot of factors, so therefore there can be error. Secondly, the objects may not have a linear density, as they can have more mass in one part of it than the other. Because in this experiment we are assuming that the objects are perfectly distributed their mass along it. Third of all, our analysis could be wrong. There could be some other forces, as well as not accounting for the for air, as it's also exerting some pressure, as well as the changes in temperature, etc., etc. So more research needs to be done in order to get more correct result. But at least from the prism, it seemed to line up. But this could just be a coincidence. It could be also be affected, just not nearly as much as the cylinder. So sadly, we weren't able to prove the Archimedes principle with success, but at least we learned how it works, and we can see this in order to improve on further experiments. Thank you for watching.